Good afternoon and welcome to today's Spring Science Speak seminar. My name is Patricia Maloney and I'm the Associate Director of the UC Davis Tahoe Environmental Research Center. And to learn more about TURC, the research we conduct here and around the world, the public education and citizen science programs we provide for the community, and our work with government agencies in the Tahoe Basin and beyond. Please visit our website, tahoe.ucdavis.edu. You can also find out how to follow us on social media, how you can participate in our activities, and how to help support our activities, including these monthly lectures. One of the goals of our seminars is to facilitate dialogue and discussion. We will address questions at the conclusion of today's presentations via the Q&A function on Zoom. The best way to ask questions or make comments is to type them into the Q&A, and our presenter will try to get to them as soon as possible. Before I introduce today's speaker, I want to alert you to do some of the upcoming events that we have coming up here at TURC. On April 14th, we have Megan Collins, Dr. Robin Godner, and Dr. Allison Merriam and Megan Collins giving a presentation on the Living Snow Project. On June 22nd of 22, Nature Tells Its Story, the Climate Archive of Caves with Isabel Montañez, and that will hopefully be a return to in-person events at TURC. And on July 28, 2022 is the State of the Lake with Dr. Jeff Schlato, our director. In June of 2022 is our docent training. Dates are still being finalized. And then in June of 22 as well, you will have the circumnavigation of Lake Tahoe by kayak. It'll be the second circumnavigation, and the first one was quite successful last year. So anybody who's interested in kayaking around the lake, I would highly recommend it. It's really a wonderful way to see the lake and meet really neat new people. So our presenter today is Dr. David Jolly, who is a research hydrologist with the U.S. Forest Service Pacific Southwest Research Station. David completed his PhD in environmental engineering at UC Berkeley in 2016. His research focuses on the role of subsurface in determining water availability to forests and streams in seasonally dry ecosystems, which include the ecologically rich and winter wet, summer dry watersheds found across all of California. David and I are collaborating on a project on San Francisco Public Utility Commission's land in East Bay to evaluate drought effects on forest health, as well as hydrological consequences of San Francisco Bay watersheds. However, David and I met with colleagues from the Forest Service and SFPUC a few months ago to discuss this project, and there we learned we both had some studies out at Jerry and Ann Brown's ranch, mine on a much smaller scale and David's on a much larger scale. And David will be presenting some of that work here today. And so with that, I present David Jolly.
Tricia, thanks for the introduction. I appreciate that. Yeah, I'll talk a little bit about some of the work at Jerry and Ann's ranch. Thanks also to Heather, who put all this together. I appreciate all the organization and making it really easy. And now I know about a really cool new seminar series that is pretty diverse that I'll try to attend more regularly. So yeah, thanks again for this invitation. So I'll go ahead and share my screen here. And before I get into talk material, I just want to start by recognizing my collaborators. And so these are Dana, Daniela, Jesse, Erica, and John. And the work I'll talk about today wouldn't be possible without these really awesome scientists who kind of have their hands in a lot of different water-related projects across the state and really across the whole Western US and even parts of Canada. So mountains are really the world's kind of natural water towers. Approximately 1.9 billion people rely on their snowmelt. And even in places where snow is not common, precipitation tends to be greater at higher elevations. And so mountains provide runoff to populations that concentrate in adjacent lowlands. And the US, of course, is no exception. Some of the most economically and ecologically important river systems on the planet, the Sacramento San Joaquin, the Colorado River, the Columbia River, start in the forested mountains of the American West. And mountains are important for more than just the water that runs off of them, right? They also host some of our most cherished and dramatic ecosystems. So here I got a picture of Yosemite Valley, hopefully dramatic enough for you. But mountains around the world are changing, and the particulars kind of vary based on your location, but drier, warmer, wetter, less snowy, et cetera, all these different options are kind of on the table. In the Western US, our best projections of climate tell us the following: temperatures will be higher and precipitation will be more volatile. So that is, to kind of translate that, the expectation is that kind of the average precip won't necessarily change a lot, but we will have more frequent extremely wet seasons and extremely dry seasons. And so in California, we don't have to look far for examples of this increased volatility. The previous decade has given us the driest string of years on record that we have, with massive tree die-off in the Sierra Nevada. And in 2017, we witnessed the single wettest year on record, during which we barely avoided the catastrophic failure of the spillway in the Oroville Dam, which holds back the state's second largest reservoir behind Lake Shasta. And some of you are probably also thinking about the emotional roller coaster of a wet season that we've had this year in California. Here I'm plotting right now only in October, but I'll go through the season, historical average precipitation in blue, so that blue point with the standard deviation in that little blue bar near Truckee, California, so up near Lake Tahoe. And then the observed precipitation for each month this year. And so starting in October, parts of the Sierra received 15, even 20 plus inches of liquid of precipitation fell over the course of more or less a single storm event, a multi-day storm event, shattering precipitation records across the state for that month. This was followed by a real bust of a November with total rainfall in the kind of single-digit percentiles. And then the wet season roared back in December, producing near record liquid totals, and record snowpack was actually measured at the Central Sierra Snow Lab, again, up near Truckee. And it's a good thing that December was as big as it was. Across much of the West, we've had the driest January to March period on record. I haven't plotted March yet because the data set that I was using hasn't quite come out with it. But it's not going to make things look any better here. You can see that we're really pretty catastrophically below average in terms of the amount of precip that we usually get in the first kind of handful of months of the year. So zooming out a bit, with all this volatility, especially drought, there's been a lot of kind of retro and introspecting going on about reservoirs, hydrological infrastructure, agricultural water use, et cetera. However, I'm with the Forest Service, so as you might guess, I'm really interested in our trees and the mountain watersheds where they live. One theme that has emerged in post hoc analysis of the most recent 2012 to 2016 California drought mortality event is that predicting the biogeography of tree mortality, that is the kind of spatial distribution of where trees died and where they didn't, using plant physiological factors alone does not work so well. So the question is, what makes mortality prediction so hard? Well, the answer to that is pretty complicated. For example, proximate causes of tree mortality, like pests, bark beetle, for example, are not well understood. However, there is a fundamental variable that's sparsely documented, yet it really kind of sets the stage for most large-scale tree mortality events, and that's subsurface water availability. Whether or not climatic drought results in ecohydrological drought is really a subsurface question. Plants don't care how much it rains per se, they care how much water is stored in their root zone. And in our winter, wet, summer dry Western climates, trees must dig really deep for their water, typically way beyond the thin upland soils that we found in mountainous regions and into the weathered, fractured bedrock beneath, where plant available water is stored as unsaturated moisture held in rock or as saturated groundwater in fractured bedrock aquifers that actually are the primary mode of streamflow generation in these watersheds as well. And just a note on terminology, when I use the word unsaturated soil or unsaturated bedrock, what I mean is the soil or rock holds moisture, but that moisture is held under tension, like soil, water in a houseplant that's not dripping. In contrast, if you were to hold a block of saturated material, you'd find that that saturated material is dripping out the bottom freely. So to calibrate our eyes a bit to this kind of root zone story that I'm starting to tell, I've illustrated what the root zone looks like using a cartoon hill slope cross-section, which is representative of what we commonly find in upland mountainous regions: thin soils underlain by a thick layer of weathered bedrock, then at a certain depth, highly impermeable unweathered bedrock that sets the bottom boundary for our forests. So today's talk, I want to sort of address three pieces. One is, where is the storage in the subsurface that matters for trees, for understanding tree response to drought? And how does this storage determine how trees experience drought? And then finally, how does this storage also play a role in dictating how streams respond to drought? And the story is a little different in both cases, so we'll kind of get into the particulars of a couple of case studies. And I'll start by just pointing out probably the most important kind of subsurface parameter or characteristic for understanding how trees experience drought, and more broadly for understanding the water budget of our forests. And that's the root zone water storage capacity. And this is the maximum volume of water that can be stored below ground that's accessible to vegetation. To understand why the root zone water storage capacity is so important, I'm going to rely on a pretty simple but actually surprisingly accurate analog, at least in terms of the physics and underlying observations. And that analog is the wetting and drying of a kitchen sponge. So anyone who has clean dishes is familiar with the fact that a sponge can only hold so much water, a storage capacity, if you will, after which additional wetting of the sponge results in dripping. And at nearly every site, there's a little bit of a simplification, but not that much. At nearly every site where we've directly observed subsurface water storage and subsurface flow paths, this drippy sponge analogy is actually more or less how root zone water storage and runoff generation works. The root zone sponge fills, drips excess inputs that recharge shallow groundwater systems that feed streams. Of course, if you've ever watered a houseplant, you've seen something similar. The soils soak up a certain amount of water. They hold that water without dripping. But after a point, any additional irrigation from the water can ends up just making a big puddly mess around the base of your pot. So once the sponge finishes dripping, it nevertheless remains wet, right? So only transpiration / evapotranspiration, so that's, abiotic evaporation, water sort of leaving the near surface of the sponge, or transpiration, which, is tree water use, potentially occurring much deeper. Only those processes can really fully dry out the sponge. And so the storage capacity of the sponge is really one of the major factors that determines how much moisture is available for plants to transpire and how much precipitation or snowmelt is required to pay off water debts generated during the dry season. So I was looking over here at some of I'll just pause really quick for some of the Q&A. Maybe I'll try to address some of these as we go along. Maybe we'll see, I don't really know. I've never used the Q&A function before. So under what scenario would we see a drastic lowering of the water table? That's a really good question. We'll get to water table stuff, I think, in a little bit, hopefully answer that. Actually, maybe I won't answer questions because I'll totally get derailed. I'm very distractible. I'll just stay on task for now, and we'll try to get to all these at the end. So back to slides. Unfortunately, this sponge analogy breaks down when we try to think about how to actually measure root zone water storage. This is a cryptic and difficult to observe variable in situ, especially in weathered bedrock, which you might imagine. And this is evidenced by the frequently labor and time intensive instrumentation that we have to use to actually measure subsurface water storage. So the question is, how can we estimate key water storage properties at the scale of national forests, right? The scale that matter for management decisions and for understanding how forests as a whole work. And what can estimates about water storage capacity tell us about how forests and streams might or might not be resilient to drought. So one way we've addressed this observational challenge is to use rapidly advanced, remotely sensed data sets of precipitation and evapotranspiration being tree water use, to track what I'll refer to as the root zone water storage deficit. And the root zone water storage deficit is really just a measure of how dry the sponge is. To illustrate the basics of the method, I'll ask that you flip the way you think about storage a little bit. Instead of thinking how much storage trees have, I want you to think about the net amount of water that they have lost from their root zone over time. And the helpful metaphor here before I go through this animation is a credit card balance. Debt owed is the net of withdrawals. In this case, the withdrawal from the root zone is transpiration, which you'll see in the top plot here in green, and deposits. And deposits in this case are precipitation, right? The amount that you're sort of inputting into the account. And that'll be plotted in the middle plot over time. So let's play this forward, where I'll plot the size of the deficit down on the bottom plot in orange. And what you can see is the water storage deficit grows, right, when the outputs, evapotranspiration, exceed the inputs, precipitation. So when the green is bigger than the blue, you accrue a bit of a deficit. You're building your debt. The opposite happens, right, when inputs exceed outputs. In that case, you can cancel out some of your debt. And the cool thing about this approach in general is we can kind of just track it forward through time with these really amazing remote sense data sets and answer a couple of important questions. One question is, at any given time, how dry is the sponge? And then over a really long period of record, we can also look at what was the largest observed water storage deficit that we saw. And that really puts a constraint on how big the sponge is in general, right? The largest kind of deficit we see puts a lower bound on how big that sponge must be. And so what can we do with this nifty remote sensing way of looking at water storage? Well, until recently, most scientists thought of plant rooting in bedrock as a sort of ecological oddity, that maybe plants used bedrock water storage, as a last resort during drought. While that may be true that plants rely on bedrock water storage during drought, Erica used a storage deficit approach that I'll go through in a minute to prove that bedrock water storage is actually an essential and regularly accessed component of the root zone sponge, and that we need to dig beyond shallow soils into the bedrock beneath to fully understand the day-to-day use water habits of trees. To show this, Erica first assumed, pretty defensively, I think, that root zone storage is really just the sum of water stored in soils and water stored in bedrock, which when you pair this with the deficit-based estimate of total root zone water storage capacity, provides a bound on how big the bedrock water storage zone must be. This is a bit of an oversimplification, but the method is basically, if I take 8 units of water out of the root zone and the soil can at most hold 5 units of water, then I must have gotten those additional 3 units from somewhere else. So that's kind of a simplification of how the calculation works, but that's more or less what we did. And the findings in California were especially striking. Almost without exception, upland forested parts of the state rely on bedrock water storage every single year. And we've indicated that here in this map in green. So the sort of bedrock water is reliably used every year is mapped in green, some years mapped in purple, not necessarily used, but maybe in black. And then there are a lot of places, forested places, where for a number of reasons we couldn't classify because we wanted to be cautious. Importantly, in California, we found that the water stored in unsaturated bedrock actually generally greatly exceeds the water storage capacity in the overlying soils. And that bedrock water storage, when you kind of do a fun calculation, is just about equal to the water storage in total of all of California's surface reservoirs. So Shasta and Oroville and all these lakes, if you add it all up, it's about the same. So that's a cool finding. And I want to move on to a second piece here to address how the root zone sponge tells us more about kind of the sensitivity of forest to drought. So knowing the size of this sponge can really tell us more than just like where do the trees access water. And some of the findings that I worked on with my colleague Jesse in this paper 2019 that we cited in the bottom left, were a little counterintuitive. For example, we found that small water storage capacity relative to average rainfall can actually lead to an increase in the resilience of plants to drought. So that might seem a little backwards. You think maybe a big bucket would be good. And the manuscript presents a proper hydrological model to explain this somewhat counterintuitive finding. But falling back on the sponge analogy, which is very reliable, if the sponge is small enough, both dry and wet winters will fully wet the sponge. And so storage will actually be the same from year to year, even if precipitation totals exhibit really large variations. This suggests a purely hydrological mechanism of drought resilience, which we've termed storage capacity limitation. The flip side, right, is the case of the big sponge, which we'll refer to as precipitation limited. In this case, more precipitation results in more storage because the sponge can accommodate it. Less precipitation results in less storage. And in these places, we would predict increased sensitivity to the swings in annual rainfall. This way of thinking about forest resilience may help to explain some previously unexplained patterns in tree mortality in the most recent drought. A post hoc modeling exercise by Young et al., which I've taken a figure from here on the left, revealed really large error in predictions of tree mortality in many Northern California forests. Despite receiving half of mean annual rainfall during the peak of the drought, almost no mortality was observed in these places. So what's going on? So actually, we have a couple of field sites in Northern California where we were, during this period, monitoring tree species, a number of tree species over the course of the drought. One site, an oak savanna, the other site, a broadleaf, needleleaf, evergreen forest. And because I thought I'd kind of show you a little bit also kind of how we take some of these measurements in this talk. We quantify tree water stress using what's referred to as a tree water potential. And a tree water potential is really just a measure of how hard a tree is having to pull to extract water from the dry subsurface sponge. And the measurement itself is pretty cool. I have a schematic here in the center where you'll see a leaf inside of what we refer to as a pressure bomb. It's really just a really burly metal chamber. We stick the leaf inside of it, and then the stem of the leaf is sticking out of the chamber. And we then have this really high pressure nitrogen tank that we take with us out into the field, and we start to increase the pressure inside the chamber. And when the pressure inside the chamber equals the tension, the strength of the pull that the plants were having to exert to get water out of the dry soils that are holding onto water very tightly like a dry sponge. When that equilibration happens, what you actually see is sap water reverses out of the leaf. And so as soon as you see water start bubbling out of the stem of the leaf that's kind of sticking out of this pressure chamber, you take a reading of the pressure at that point, and that pressure is actually exactly equal to the tension that the plants were exerting to pull water from the subsurface sponge. So it's a really cool measurement. It's very easy to take, and it's actually very powerful. And you can use it on all sorts of different tree species. It's also used in viticulture and different fields where, you know, folks need to know on a regular basis how stressed or not are their plants. And just a quick aside, in viticulture, sometimes it's good to have stressed plants because that might introduce new flavors into your wine that you want. So these things are actually really commonly measured in more like industrial ag settings too. And so here I plot this water potential across a collection of trees at each site at the end of the dry summer for 2 years. The record drought year in 2015 and the record total rainfall year in 2017 that I mentioned earlier. The first thing that we notice, and that this plot here, right, I have an arrow showing that the farther left you are, the more water stressed the plant is, the harder it's having to pull. These units here, this pre-dawn water potential, you can ignore that, but it's units of pressure, how hard the plant's pulling to get their water. The first thing you might notice is that the oak savanna, the red dots, are always more water stressed than the forest. And so that's not necessarily a bad thing. The oaks at these sites are adapted for high water stress, so they're prepared for it. The interesting part of the plot instead actually is the difference within sites between these 2 years. Or rather, if you're looking at the plot, the lack of difference. In both the record wet and record dry years, water potentials were statistically indistinguishable at these sites. Not only did the trees not die in drought, they actually never really even knew a drought had occurred, at least insofar as their water stress is kind of indicating how they're feeling, to anthropomorphize the trees a bit. So how does this like total insensitivity to water availability, or rather precipitation, occur? During her PhD, Daniela pioneered geophysical methods for measuring deep water storage in the root zone. And in a 2018 paper, she presents direct observations of water storage in bedrock through time at this forested site. And some of her data I've included here at the bottom, plotted. You'll see on the vertical axis is water storage in bedrock, and on the horizontal axis is cumulative seasonal precipitation. So you can kind of think of, as you move to the right on these plots, the wet season progressing, you're accumulating more rainfall as the kind of winter wet months carry on. And then the vertical axis tells you how much storage you've accumulated over that same period. And the thing to notice in these plots is how water storage in the rock, the vertical value on the axis, on the value on the vertical axis, at the forested site initially increases as precipitation increases. But after a certain point, adding more precipitation does not result in additional storage. The relationship totally flattens out, and storage becomes what I'll refer to as decoupled from rainfall. And this is a direct observation of the storage capacity limitation mechanism actually happening in bedrock. This is the sponge filling up to capacity and then dripping. And in this case, the sponge is much smaller than the pitcher that represents kind of our average rainfall year. And so the sponge will fill up to capacity in both relatively wet and relatively dry years. And so I'll just really quickly note, this is at the forested site, and I won't go into it here, but the Oak Savanna site has an analogous water storage dynamic happening also, but for very different reasons that results in an even smaller water storage capacity. That's for another talk, but if anybody has questions about it at the end, we can maybe revisit it, because it's a cool story there too. So we wondered whether apparent resilience of many Northern California forests might be explained by this storage capacity limitation mechanism. And Daniela's work gave us a really nice test for identifying the condition itself. And the test is plot storage versus precipitation. And if you see that storage in the sponge from year to year sort of heals over and is independent of the final value of annual precip, which is here the value on the horizontal axis, you've got a storage capacity limited case on your hands. And since trees rely on this storage over the course of the dry season, we hypothesized that in places where we see this healing over of storage, the storage capacity limitation type behavior, we would also see that forest productivity is completely independent of total precipitation in both wet and dry years. This effective kind of hydrological shielding of forests from large swings in total rainfall experienced in drought. And that's what we see on the top plot here for Elder Creek, which is the forested site. Each year, no matter the precip value, the storage is roughly the same. Consequently, on the bottom row, no matter the total volume of precip that falls, vegetation response is also more or less the same. There's a really weak trend there that's kind of statistically negligible. So we took this approach on the road, testing for storage capacity versus precipitation limited type watersheds, and actually ended up finding a whole spectrum of behaviors. It was kind of cool. On the left, we have Elder Creek, a representative storage capacity limited site. And without exception, in places where storage is insensitive to precipitation, as we see in the Elder Creek column, trees were similarly insensitive to variations in annual total rainfall. Conversely, in places where storage was sensitive, the precipitation limited sites, represented here using the San Lorenzo Creek site on the right, we saw the annual variations in precipitation led to greater or lesser amounts of vegetation water stress. Those are really cool. So it's kind of this suggestive of a pretty strong subsurface control on how rainfall gets translated from year to year into water availability to plants. And so we were able to observe this storage capacity limitation mechanism in action at our Northern California sites, which I previously mentioned. But the precipitation limited sites remained a little bit of a mystery to our group. However, it's precipitation limited sites, of course, where trees are dying in drought. So what's happening inside of hill slopes in these places? And this is to call back to Trisha's mention at the beginning. We're now going to focus on a site, Rancho Venada, which is the Brown Ranch. It's in Colusa County. It's in the eastern part of the Coast Ranges, so kind of an hour-ish north and west of Sacramento. And the question of precipitation limitation motivated our recent move to this site in 2018, where reconnaissance and precipitation records suggested we might see precipitation limited storage dynamics. So we went to the ranch, we drilled, and we began similar monitoring as the Northern California sites that I mentioned earlier. And it didn't take long for a very real test of the principle that I outlined. The first 3 years at the site, we went from a fairly wet year in 2019 to 2 record-breaking drought years in 2020 and 2021. And of course, I don't have the data here, but 2022 is not looking great either. From our measurements, we have plotted here, I've plotted the estimated water storage capacity in red. And interestingly, the site appears to be a bit of a shoulder case. So not quite Elder Creek, not quite San Lorenzo Creek. It's somewhere between storage capacity and precipitation limited. So some years precip appears to exceed storage capacity, other years no. No years, however, were more precipitation limited than the record-breaking drought years of 2020 and 2021, these recent water years, during which we experienced really unprecedented low rainfall totals. So what happened below ground? I haven't plotted it here, but we found that rain was sufficient to recharge the thin soils at the site, which are between 40 and 100 centimeters thick. So if you were just measuring the upper soils at the site, you'd think things were just fine. And I forgot to mention, if you look at this picture here, this is actually like a hill slope cross section that is generated from real data. The weathered bedrock is this kind of yellow fracture-y looking stuff. The gray bedrock is the unweathered stuff. And then the soil is that really thin light brown veneer on top of everything else. So this gives a sense, and the green dots are the oaks. So this gives a sense really the scale, right, of how thin the soils are relative to the weathered bedrock layer. So yeah, sorry I didn't point that out. So despite this wetting in the upper soils, what we found was a consistent deep dry down in the weathered bedrock that progressed over the course of the drought. And taking all the observational borehole data across this site, we can calculate a sort of hill slope scale water storage time series plot, as I've shown here in the bottom. And so the thing you probably want to focus on most is the dotted line, which is the average of water storage across all of the observational boreholes. And so what you can see is we reached water storage capacity. So we kind of maxed out water storage in 2019. There's that first peak. But then we only saw about half filling of the bedrock portion of the bucket in 2020. And we saw almost zero precipitation reach the bedrock portion of the bucket in 2021. So the true underpinnings of ecological drought at this site are the water storage dynamics in the deeper weathered bedrock. So what are the consequences for the oaks? Well, in 2020, we got partial refilling of the deeper bedrock, and the drought tolerant oaks were able to get by in that year. Leaf out occurred, sap flows were only somewhat depressed. The second year of deep drying, however, is a different story. Many of the oaks did not leaf out during the summer growing season. Significant crown dieback has occurred for some individuals, and we continue to monitor the situation, but are unsure how things are really going to pan out, especially with the continuation of drought this year. Aerial photographs from the 30s, I'll just note, show that all these oak individuals have actually been here for a very long time. If you look at this photo from the 30s, it looks like more or less these trees are exactly the same size. That was like 100 years ago. So if we lose these oaks to this drought, it will truly be an unprecedented die-off. So we'll to be continued. We'll let you know how that turns out. So for the final part of the talk, I'll shift gears briefly, and I want to remember that root zone water storage deficits are germane to more than just the mortality story. They also mediate runoff generation. In the Sierra Nevada, snowmelt fluxes must overcome the water storage deficit before the sponge can drip to produce snowmelt runoff in the spring, a critical water flux that fills reservoirs essential to California farms and cities, as well as Lake Tahoe. The ongoing California drought provides a case in point in the form of a water supply forecasting mystery. In spring 2021, snowpack was below average, but was not catastrophic on April 1st, yet subsequent runoff was historically low. This got a lot of press, with the California Department of Water Resources Chief Water Forecaster, Sean de Guzman, noting, "We have 100 years of data saying if you have this much snow, you expect this much runoff." But that fell apart this year. So the question is, what happened? And again, deficit calculations will reveal the annual story of wetting and drying that matter for runoff. Here, I'm plotting the running water storage deficit in black. So I haven't revealed the whole plot, but we're starting here in October of 2008, just as an example year. And then I'll plot plant transpiration, remember the outgoing term in the deficit calculation, in green, and precipitation, the ingoing input term, in blue. And at the end of a long dry season, the onset of the wet season, deficits start off really high due to the previous summer of plant water use. And as precipitation increases and the wet season gets going, the deficit shrinks, the sponge is being refilled. Finally, the deficit with enough rainfall is totally zeroed out. And by the drippy sponge principle, this is a prerequisite for significant runoff generation to occur. So if you want to really understand how much water makes it to streams, the key consideration is, what is the size of the water storage deficit on October 1st relative to that year's precipitation and snowmelt? These two things kind of considered together in a ratio type way is really the correct way to kind of consider how much water might actually end up making it to streams. And just I'll note finally, this whole thing repeats from year to year. The deficit will grow again in the subsequent dry season when evapotranspiration again begins to exceed precipitation. And a reminder, I keep beating this drum and I'll keep doing it. The deficit that we calculate every year in most of these watersheds around Lake Tahoe and most of the Sierra almost always exceeds the mapped soil water storage capacity. And so to explain this runoff story, we must also invoke a water storage and weathered bedrock argument to understand where runoff might be going, or rather where it might, where snowmelt and precipitation might be going instead of streams. So Dana, if it loads, there it goes. Dana used the data that I just illustrated to develop a deficit-based streamflow model for predicting snowmelt runoff every year in the spring. Her model not only significantly improves prediction in small and large Sierra Nevada watershed basins, including many basins that are critical to California water supply, it does so with minimal inputs and assumptions. It's really kind of more of a mass balance based model as opposed to a full-blown hydrological model, which requires all this additional data input and because of that additional uncertainty. And her model helps us to sort of, with these minimal assumptions, attribute any missing runoff to different factors. And that's what's going on here in this plot to the left, which you can think of as a sort of pie chart showing how important different terms are in Dana's models. Black and red show the relative importance of each term in wet and dry years, respectively. So the terms that we're considering are winter rainfall, the deficit on October 1st, the start of the wet season, spring ET, so that's plant water use in the spring, winter recharge, so that's how much might make it to the groundwater during the winter. And then the last one is the melt rate. So that's how quickly does the snow melt in the spring. And all these things have been tied in various ways to runoff, but they've not necessarily all been compared within a single framework. And of course, what kind of pops out right away is that winter precipitation is the most important term. So that's good, it makes sense. But second to that was this deficit term, the importance of which was nearly as large as precipitation following drought years. So the red, right, is the year following a drought. So the importance of the subsurface storage deficit is really elevated during particularly dry periods. And the take home is that California's missing flow in this recent and now ongoing drought actually served to replenish water storage deficits that were generated in deep soils and bedrock in the previous growing season, owing to low rainfall and warm summer temperatures. So Dana's kind of working on wrapping up this particular manuscript, and it's preprint right now. You can find it at that link if you want to, and hopefully soon it'll be in submission. All right, so we're kind of getting towards the end here, and I'll just list a few take-home points. So the big things that I hope you walk away with are, first, that root zone water storage deficits are really new, not necessarily new, but because of the data sets that we now have access to, are a increasingly powerful organizing framework for understanding and predicting how trees and streams experience drought. And soil and bedrock water storage are required to explain the magnitudes of the deficits that we observe. So in particular, water storage in bedrock is a sort of an unmeasured zone that requires more attention if we really want to understand the water balance of our forests. And just a more general call, half our forest is underground. So we need to dig deeper and peer inside of hill slopes to understand the future of water resources. And if you're interested in learning a little bit more about this deep subsurface story and how it pertains to trees and streams, there's a really cool paper that Todd Dawson wrote with Jesse and a couple other folks in 2020. I can provide a link to that in the chat, where they really talk about this kind of deeper unmeasured zone and its relevance to understanding hydrology, especially in California. Great, so that is all the material I have. So it looks like we took about 40 minutes. So that's good, we have plenty of time for any questions and discussion. And feel free to reach out to me via email if you have any thoughts or questions that I haven't answered here today, or other things that you'd like me to follow up on. I'm available. Thank you. And Heather, I don't know if you want to field questions, or if I should just go down the list.
Yeah, I wasn't sure if Trisha was going to field them,
okay.
But you started to talk about under what scenario would we see a drastic lowering of the water table, and is it conceivable to run out of fresh water? You started to talk about that.
Yeah, so just the key there is the water table. If I could just zoom back. In most places where we've really dug deep and gotten a picture of how things work, this is the best picture I've ever seen for explaining how runoff generation works in montane watersheds, especially in the American West. Thin soils, thick weathered bedrock, and a deeper groundwater fractured bedrock aquifer that feeds streams. And if you remember, the sponge only drips when it reaches capacity. And so this groundwater reservoir only experiences recharge when the root zone sponge has been fully replenished. And so in drought, this is the mechanism really of, you could think of it as trees stealing the water from the stream. I don't really think of it that way, but and we could get into a big discussion about sort of how our forests are overstocked in many places, which they are. But really it's this recharge term that I've illustrated here. That only really happens when the root zone sponge has been fully satiated, when the deficit has been canceled. And so I don't know about the necessarily running out of fresh water per se. There's always going to be water somewhere down there. But whether or not that water can make it to streams is very much a root zone related question. And the other picture I'll show that illustrates that. This shows, again, the cumulative water year precipitation 2019, 20, 2021 at our Rancho Venata site, the Oak Savannah site. And only in years where this root zone water storage capacity is exceeded by rainfall do we actually see flow in the streams. It's really cool. Like, it works really, really well, just as a very rough predictor. And so in these years that fall below this threshold, we just don't see flow in the streams. The years that fall above it, we do see flow in the streams. So that hopefully that provides some context for the groundwater recharge story.
Perfect. Well, Hannah had another question about what do you think of the sponge city concept? Are steps being taken to plant more trees and reduce impervious surfaces to capture more water during extreme precipitation events? And I guess my question that goes with that is like city planting, you know, what happens in cities when they're talking about all kinds of tree planting?
Yeah, it's a really good question because you can imagine it going both ways, right? On the one hand, if you pave everything, you can't store water anywhere. It's going to leave. It's going to flow. It's going to hit the storm drains, and it's going to eventually make its way to the ocean. On the other hand, if you have trees everywhere, you might imagine the trees could end up using a lot of that water as well. In general, I think that removing impervious surfaces and vegetating cities will generally lead to more water storage on the landscape. It's a good thing, but you know, it does come with the cost of, you know, having to supply water to the trees too. So you don't just get all that water for free if it's not running off over impervious surfaces. But it's a good question. And to answer it, I think you would kind of maybe need to model the hydrology a little bit to understand what that return on your investment might look like for, you know, removing a certain patch of concrete and replacing it with trees.
Yeah, our previous associate director, John Ruder, is actually doing UC Davis in Davis tree planting, city trees. So
Cool.
It's coming full circle. Mark asked the question, how does the Lake Tahoe reservoir affect groundwater in the Tahoe Basin?
Yeah, that's a really, I mean, it's a good question. And I don't know enough about the hydrology of lakes to really answer that in a super educated way. I know that the runoff story that I've been describing that is really relevant for the hill slopes that surround Tahoe play a big role in determining when Tahoe is filled by adjacent streams or not. How Tahoe itself impacts the regional groundwater system is not something I'm super familiar with. There is a lot of work on this so-called kind of mountain block recharge. So this is how large groundwater systems at really high elevation can slowly over time make their way down towards lower elevation, even as far as the Central Valley, and subsidize groundwater systems at those lower elevations. But it's definitely not my area of expertise. So maybe Google search the word mountain block recharge and kind of dig around a little bit. But yeah, it's a cool question, and I'd like to know more about Tahoe groundwater.
Okay. Hannah had another question. In areas of the world that rely on spring melt, so snow melt for fresh water, and where snowpack is disappearing, what do you predict will occur?
Yeah, so you know, the one prediction you might make, and this is relevant to the Sierra, is a lot of places in the Sierra were scraped clean by glaciers in the Pleistocene, the most recent glacial maximum. And so the water storage capacity in a lot of places in the Sierra is actually not super high. And because of that, the snowpack really does serve as a kind of above ground reservoir that the plants rely on over the course of the, you know, the kind of start of the summer months. And so the forests, in a sense, without the snowpack could not necessarily be as big as they are. So, you know, one prediction is the disappearing snowpack will require that trees are more reliant on the storage capacity of the soils and the rock, which is smaller. And so we might expect that the forest might not be able to support quite as many trees. Another kind of part of this question, though, is like what happens during the wet season if more precip is showing up as rain instead of snow? So instead of accumulating on the ground surface and slowly melting out over the spring, you just get it full-on delivery to the subsurface straight away in the winter months. And so in that case, we might actually predict a bit of a switch to some of this storage capacity and limited runoff behavior that I mentioned earlier, where the subsurface fills the capacity really quickly, additional water runs off. And so, you know, prediction there would be that the runoff during the winter months would increase. There'd be less storage in the subsurface going into the spring months, and we might expect a decrease in biomass in the forest because there's just not as much water there to support it. I guess another related thing is, like, if things really do switch to that kind of storage capacity limited way of thinking about it, the forests might decrease in size, but in a weird way, because of that, they might, these future forests might actually be more resilient to future drought. So that's very speculative. I don't know if that's what's going to happen. But it would be maybe a prediction of a kind of switch from a snow dominated to a more like a rain dominated type mountain environment.
All right. So Aaron has a question about your wells. Can you tell us more about how you used your wells, such as looking at drawdown and static measurements?
Yeah, that's a cool question. Now we're getting into the questions I like. Let me see if I can, mostly because I like nerding out about the methods. I'm trying to see if I have a good slide here that shows a nice picture of our wells. I'd say I don't really see anything good. We use the wells in two ways. I guess I'll just rely on this, my hill slope profile picture. We use the wells in two ways. The first way that we use the wells is to just find out where the groundwater table is. And we have ways of measuring the porosity of the subsurface material, so we can translate the height of the water table into an actual total storage of water, right? Because not the water table is this thick, not all of that thickness is liquid, right? A lot of that thickness is just rock. And so you have to subtract out the rock to know how much water you have stored. So we learn that in our groundwater wells, and we watch the groundwater dynamics from year to year, from storm to storm. And that's how we know that the groundwater is really the dominant driver of stream flow in a lot of these places. As we watch these observations, you can do mass balance and say there's this much in the stream, this much just disappeared from the groundwater, put two and two together. The other way we measure, or the other way we use the wells, and this is really important, is we use them to measure water in the unsaturated zone, so not the groundwater. And I had a picture of Daniela here where we use this tool here called a Neutron Probe, and it's a lightly radioactive probe that shoots out neutrons, and then the number of neutrons that kind of bounce back that the probe can detect is inversely proportional to how much water is there. And the cool thing about the Neutron Probe is it can be used. You can just drop it down a groundwater well and it shoots all these neutrons out, and then they come back and you know how much water is in like a beach ball sized kind of integrating area around the probe itself. This is important because this is really the only way that we know how to reliably measure water storage in the bedrock. You can't use the methods that are commonly used in regular old soils to measure water storage. Soils are more accessible. You can stick all sorts of probes into them. It's actually relatively easy to measure water content in soils. You need these geophysical tools to measure water storage in bedrock. So that's another way we use the wells. And that's how we're able to measure this rock moisture storage term. And that's how we're able to attribute the tree water use patterns to the water storage dynamics in the bedrock, is using this Neutron Probe tool.
So along with that question, John asked, do we have many wells other than domestic water wells in the Tahoe region that help us monitor the drawdown during the year?
Yeah, there's a lot out there. I mean, there's academics that have their own wells. I know a few people that have wells at different sites. I'm less familiar with who's doing work around Tahoe. The one place that is very well instrumented is the Sagehen Creek experimental station. So there's some work going on there on groundwater. I don't know if they have super deep wells there or what exactly they're doing, but I've been meaning to talk more to those folks. And Yeah, in general, it's, groundwater is a very sparsely observed thing. There's more measurements of groundwater than rock moisture, because you don't need necessarily the fancy radioactive tool to measure it. You can just drill a deep hole and see where the water surface is. So they are more common than that, but they are not necessarily ubiquitous. Yeah, the ownership is, mixed. There's domestic, there's ag users, there's, random people with their drinking water wells, there's academics out there. But as far as I know, there's no like really great centralized database. The USGS, I'd say, would be your best shot for looking at wells that are public, but yeah, it's a good question.
Yeah, they should make like a snowtail site, but of groundwater.
Yeah, that'd be nice.
So Aaron has another question about during droughts, can we expect any concerning subsidence, is that the right word? Similar to that of extracting groundwater via agricultural wells, where aquifers don't fully recharge because the ground is more compacted?
Yeah, that's a cool question. So in ag settings, like Central Valley, pumping of aquifers results, two things happen when you pump a groundwater system that has been wet for thousands of years. You remove the water from the system, and things are buoyant when they're in water, right? Including soil. And so if you pump a groundwater system, you dry it out, you're actually effectively increasing the weight of the aquifer material that was hosting that groundwater. And now, because it weighs more and it's a compressible soil-like material, it starts to smush itself. And that smushing, that self-smushing of the aquifer material is not reversible. You try to put water back into the aquifer, it doesn't necessarily pop back up. That porosity can be forever lost. And there are really dramatic examples of this happening in the Central Valley, where subsidence has resulted in the drop of farm surfaces, like literally the elevation surface, like dropping tens of feet. And there are some probably find a picture of it. Subsidence Central Valley. See if there's any good ones. Yeah, this is cool. I mean, this is really dramatic, but like, this is where the ground surface was in 1925. This is where the ground surface was in 1955, 1977. It's lower today. So it's like literally the whole valley is dropping. This is not as common in upland settings because the main aquifer material is fractured bedrock. It's far less compressible as an aquifer compared to soils and more like alluvial Central Valley type settings. And so we don't quite see the same level of subsidence. And that groundwater use question is also, it's not quite as dramatic in most parts of the mountain. Moreover, hill slopes are relatively isolated. Like if I pump groundwater from the Central Valley, it affects a really large area around me. Hill slopes are kind of like little isolated units. And so pumping here definitely impacts what's happening in the stream, but it might not necessarily have an impact on, my neighbor's hill slope over there. It's a more complicated question, but I guess the short answer is subsidence not as common in mountain sort of bedrock aquifer settings.
Perfect. Well, that was all of the questions, and we're right at 1 o'clock. So that is perfect timing. Thank you so much for your presentation and your time. And thanks to everyone who joined.
Thanks,
and this will be recorded and available. Trisha, do you have any closing comments?
No, that was great, David, and thank you. My only one comment about Jerry and Ann Brown's ranch is that what's unique to it as well, and why that system looks so stressed, is that it's almost, there's a double rain shadow effect going on at his ranch, as you move across the Coast Range and stuff, and Clear Lake and whatnot. It's almost like it does it twice. So it's almost like it's a double rain shadow of having like the east side of Tahoe, doing that twice. And so it makes it exceptionally dry there. But yeah, but that's it. Thank you, David, so much.